to be in. There we go. So thank you so much, Dr. Cabetti, for that introduction. It's so good to come back home and see your faces in the meetings and seminars that I give every day at NASA Goddard. I don't see faces like yours. So it is really like medicine to see you all and to be back home. Dr. Cabetti, Uncle Marcus actually retired. So Dr. Cabetti was talking about one of my uncles who was a math professor for decades at A&T. So anyway, as Dr. Cabetti mentioned, I am Dr. Lene Quick from NASA's Goddard Space Flight Center in Greenbelt, Maryland. I am a planetary scientist. I study the planets, moons, asteroids, and comets in our solar system. I'm also was just named the associate branch head of the Planetary Geology and Geology, Geophysics, and Geochemistry Lab. And so today I'm going to talk to you about cryovolcanism on ocean worlds near and far, and NASA's upcoming Ocean Worlds mission. So I'm not sure how you all do if you want to ask questions and stop me, or if you want to wait until the end. I tend to talk pretty kind of fast, so we'll just keep going, and if you we'll deal with the questions whichever way you all want to deal with them. So here's an outline. There are a lot of words here. We're going to first talk about volcanism in our solar system, because that's fundamental to understanding cryovolcanism and what cryovolcanism is and where we find it. We're going to talk about my favorite moon in the solar system, which is Jupiter's moon, Europa. We're going to talk a little bit more about cryovolcanism. Maybe it's a major problem, maybe it's not. We'll talk about a model that I've been developing to model cryolava domes on Europa. Then we'll get into two of NASA's newest missions to ocean worlds in our solar system. NASA's Europa Clipper mission will be taking a spacecraft to Jupiter's moon, Europa. I'm very excited to be a part of that mission. And NASA's Dragonfly mission will be visiting the largest moon of Saturn, which is Titan. And then we'll touch on extrasolar planets. So here we go. All right, so in order to understand cryovolcanism, we really have to understand traditional volcanism. And I like to give this primer because I know that many of you probably know about volcanism, but this being a physics department, I like to kind of boil it down in its simplest terms. And this is, when we think about traditional volcanism, this is the type of volcanism that we're used to on Earth. It's a type of volcanism that once occurred on Venus and Mars, and that's currently occurring on Jupiter's moon, Europa. And so if we boil volcanism down to its simplest terms, I like to think of volcanism in terms of effusive volcanism and explosive volcanism. And when we think of effusive volcanism, what we think about is what we see on the top left. Effusive volcanism, the molten rock is mafic. It's a mafic lava, which means it's just a lava or a magma. Lava and magma, same word. Magma is the molten rock in the interior of the planet. Lava is the word for once it erupts. But it's a magma rich in iron and magnesium. It has less than 55% silica. The eruption temperatures are pretty high, over 1,000 kelvins. And these are low volatile content, meaning not much gas, and low viscosity eruptions. So when we look at the top left and we see this Hawaiian eruption, this pohoihoi that's just meandering across the surface, not bothering anybody, that's effusive volcanism. When we think about explosive volcanism, such as we see in this picture here on the bottom, the lava or the magma there is felsic lava, such as rhyolite or dacite. This is magma that's rich in aluminum, potassium, and other elements. It has much more silica in it than mafic lava does. It has lower eruption temperatures, and this produces high volatile content, very gaseous, very high viscosity. The viscosity of the magma is very high in these eruptions, and that's what makes them so violent. And so on the bottom left, you see Krakatoa, the volcano Krakatoa in Indonesia erupting in 1995. I'm sure a lot of you have seen images of Mount St. Helens. That's also explosive volcanism with felsic lava. So we've talked about volcanism. That's all I'm going to say about it. I feel like that's all we need to know, but we'll go and we'll explore the dwarf planets in our solar system and the moons of the giant planets, which is what my research focuses on. And you can see now here we have Pluto in the bottom right, but everything else is a moon. And these moons are dynamic, they're interesting, they're very diverse, quite beautiful. And so when we think about cryovolcanism, we'll break it down just like we did with traditional volcanism. Cryovolcanism is basically just low temperature eruptions of aqueous solutions, salts, vapor, and crystalline ice. And it occurs, like I said, on the icy moons of the giant planets, Jupiter, Saturn, Uranus, and Neptune, and the dwarf planets such as Ceres and Pluto. And so what we're thinking about is ice-like slurries in some cases. In some cases, we just have a very brine-soaked aqueous solution, so water with maybe a lot of table salt, for example, is what we have. And check out these eruption temperatures. The eruption temperatures for cryovolcanism are between 70 Kelvin and 273 Kelvin. We know, of course, on Earth that at 273 Kelvin, we start to get ice. But these temperatures are considered boiling hot for the outer solar system, because when we get out to the moons of Jupiter, Saturn, Uranus, and Neptune, ice behaves the way that bedrock does on Earth. And they're so cold, they have these surface temperatures that range from 40 kelvins to Ceres, which is the hottest of the group, has a surface temperature of 168 Kelvin. So that's why cryovolcanism with these eruption temperatures between 70 and 273 Kelvin is considered pretty warm. And so we can break down cryovolcanism again into explosive and effusive cryovolcanism. When we think about explosive cryovolcanism, I hope that a lot of you have seen this beautiful picture that the Cassini spacecraft took of Enceladus. It's a tiny moon about the size of Texas, and it has this dynamic activity. And it took this picture. I just looked at it while I was making this presentation. It took this picture the year I graduated from A&T. So what a coincidence. But so if we have explosive cryovolcanism, we'll have geyser-like eruptions of water, water vapor. You'll have icy particles, which we call cryoclasts. If we have effusive cryovolcanism, that's what we're seeing on the bottom here when we look at these walled plains units on Neptune's moon Triton. I don't know if you can see my cursor, but you see that you have these subcircular structures that are smooth. We believe that those are ammonia. Ammonia has erupted as a cryolava, and so this is effusive, just like those Pahoehoe flows in Hawaii, just meandering across the surface, low viscosity. So we've talked about what cryovolcanism is, how it differs from traditional volcanism, and let's talk about where we found it first. We just saw an image of Neptune's moon Triton. This is Triton. I like Triton a lot because I love the color pink. That picture that Dr. Cabetti showed, I was wearing a pink shirt. I still wear pink to conferences. But this is Triton on the top right, and I promise you that Triton is a full globe. What happened was when the spacecraft was sent, or when the spacecraft got to the Neptune system, the top part of Triton, the North Pole, was in shadow. So that's why we see kind of this cutoff picture of Triton. But Triton is the first place we ever saw cryovolcanism in 1989. It has a surface temperature of 40 kelvins. We have these ammonia lavas. If we look on the bottom, and we see on the bottom left these what we call the walled plains units, and there's this smooth surface. We believe that ammonia erupted. If we look at the bottom in the center, here's kind of a 3D rendering of that, thanks to Paul Schenck at the Lunar and Planetary Institute. And if we look at the picture on the bottom right, we see these dark streaks, and these are actually nitrogen geysers. So that's your, and debris left from nitrogen geysers. So this is your explosive flavor of cryovolcanism on Triton. And so this was so exciting. When NASA saw these images, and we have this new exotic form of volcanism, icy volcanism, for a while, every single time there was a smooth region on the surface of a icy moon, people assumed it was cryovolcanism. And if you go back and look at the literature, I look at all the literature that came out, around the time I was in kindergarten and first grade, they thought that there was cryovolcanism everywhere. And once we got higher resolution images, we realized that wasn't the case. So we had to wait a little bit longer for another taste of cryovolcanism. And we got it in 2005 when the Cassini-Huygens spacecraft visited Enceladus. Enceladus, again, is a very tiny moon of Saturn. It's about the size of Texas, or about the size of the UK, whichever one you like to think of. But it has, we thought it was going to be geologically dead because it's so small and it should have released all of its heat. That's not the case. And so Enceladus's geysers are just magnificent. They're mostly composed of water ice. There's some ammonia. We've also seen rocky particles, salts, and organics, I believe, in these geysers. And the reason that it's exciting that we see rocky particles is because that's a sign that the water that is being erupted into space comes directly from Enceladus's subsurface ocean. So Enceladus has an interior structure that's not too different than Earth's. We have it's believed to have a rocky mantle, and then you have an ocean on top of that. So there's a seafloor there, and that gets all types of exciting when you think about there could be hydrothermal vents, when you think about the possibility for life. So the fact that we saw those rocky particles was really exciting. These geysers are huge. They extend up to 500 kilometers into space. They actually feed one of Saturn's rings, the E ring, with water vapor and with ice. And so, it's just really exciting to look at. Most of these images are visible images. The one on the bottom right is a UV image. I don't know if I know that many of the professors, I don't know if many of the students know of Dr. George Carruthers, who recently passed away, and he made a UV telescope. Without Dr. Carruthers, we would not have been able to see Enceladus's plumes this way. And so here's Titan, which is the largest moon of Saturn. And you can see Titan in the top right. Titan is the second biggest moon in our solar system. It's the only one with an appreciable atmosphere, and the atmosphere is so thick that we can't see through it without radar. So this image that you see here is from the Cassini spacecraft. It's a mixture of a synthetic aperture radar image and a near infrared image. And here, the colors, the different colors represent variations in composition. Blue is ice. Yellow is believed to be cryolava flows. You see at the bottom right, you have Dune Mons, which is a mountain. We had cryolava erupt and just build this mountain. You see Sotra Patera to the left. Sotra Patera is a pit. So on Earth, we know that when we have magma in the subsurface and then it withdraws, a lot of times pits are formed. We think that's what happened, and that's how Sotra Patera formed, except for the magma that was withdrawn was probably some ethane ammonia type slurry. And so remember, we talked about cryovolcanism being able to be both explosive and effusive. Well, Titan's atmosphere is about 1.5 times thick as Earth's. So any cryovolcanism that happens here it's all going to be effusive. You're not going to have the explosive type. So it's really exciting to look at. And so here's another example of cryovolcanism. This is dwarf planet Ceres. Ceres is the largest asteroid in the asteroid belt. It's also a dwarf planet. It's spinning and it's stopped. We were really excited when we saw Ceres, and this was actually a mission that I was on. The other missions happened before I had my PhD, but it was exciting to be on the Dawn mission. We sent the Dawn spacecraft to Ceres, and we saw this impact crater called Akator crater that had these two bright spots. We did not know what they were. We didn't know if they were ice or what was going on. And when we got the high resolution images, we look at the top right. One spot is actually a dome that kind of has this residue of salt around it. That's the dome is called Cerealia Thalas. The bright spot is called Cerealia Facula. And the second spot, if we look at the bottom right, is actually a collection of many wispy spots called Benalia Facula. And we believe that this is evidence of cryovolcanism on Ceres. What happened at the top with Cerealia Facula was we had this briny fluid erupt onto the surface, so very salty fluid. Because Ceres is 168 kelvins, remember that's very hot for the regions of the solar system that I think about, the water sublimated and it left this residue of salt. And we've looked at this with our infrared imagers, and we got the composition, and we know these are sodium carbonate salts actually. On the bottom, what we think would happen with this wispy material is we can actually model if we just use your calculus-based physics equations for ballistic transport. When you think about parabolic motion, we can use that, and that's exactly what I used to see if we could throw ice particles and salts with an explosive eruption onto Ceres' surface and get these patterns. And so that's what I modeled in Quick et al. 2019, and we found out that's exactly what it was. We believed that we had geysers there that were throwing ice and salt out. The ice sublimated, and we were left with these wispy patterns of sodium carbonate salts. That's what formed Benalia Facula. So that's really interesting. We also found out there was a low density region, which we believe is just a large region of brine right beneath this crater. And that's the chamber that these eruptive products came from. So we've talked about a lot. This is by no means an exhaustive list. We haven't talked about Wright Mons on Pluto, which, you know, being in North Carolina, you all are in North Carolina, and the Wright brothers, I probably should have talked about that. Wright Mons is a dormant cryovolcano. And it's in here in this kind of at the bottom of this heart-shaped region of Pluto called Tombau Regio. We didn't talk about Charon, which is Pluto's moon, also has evidence for cryovolcanism. The moons of Uranus also have evidence for cryovolcanism. So it's widespread, and this is just a graphic showing some of the places that we talked about and everything that's manifested as effusive or explosive cryovolcanism. Note on Ceres, which is the place we just left. Here are the bright spots, if you can see my cursor. We also have a cryolava dome. We have a mountain that I didn't really talk about. Okay, so we've talked about cryovolcanism. We talked about what it is. We talked about where we find it. So let's talk about Europa. Europa is my absolute Europa is one of the 4 largest moons of planet Jupiter. You can see this kind of white globe, that's ice. Europa has an icy surface. It has lots of cracks and streaks and fissures. And those cracks and streaks and fissures are there is a subsurface ocean underneath. It's a salty ocean. And because Europa sits in the middle of Jupiter's big magnetic field, when those salts and everything deposit onto the surface, they're stained reddish brown. So that's what you see here. Similar to the Earth, when we think about it, you know, we call it an icy moon, but really and truly it's 90% rock, it's only 10% water. And so from the inside out, Europa has an iron core, a rocky mantle, and then it has a water ice layer that's between 100 and 150 kilometers thick. We're not sure how much of that layer exactly is liquid water, how much of it is ice, but recent models show that the outer ice shell is about 30 kilometers thick. So that leaves room for an extremely deep ocean, an ocean between 70 and 120 kilometers deep. If we look at this picture on the bottom, Europa is slightly smaller than Earth's moon. You see the acceleration due to gravity, 1.3 meters per second squared, surface temperature, that it may be the only other body in our solar system where we have a plate tectonic cycle. So we know on Earth that the tectonic plates slide past each other. We have these breaks in the crust, and we have a few tectonic plates that slide past each other. We have tectonics on other solar system bodies, but we don't have tectonics broken up along plate boundaries anywhere else except for Europa, and that was very exciting to learn. And so here's just a movie, if it'll play. If we took all of the water and all the water from Earth, put them into little globes, this shows what happens. And Europa is a lot smaller than Earth, but it has just a little bit more water. And so that's really exciting. And that's one of the reasons why we want to send a spacecraft there again to study it. One interesting thing about Europa and what allows it to keep an internal ocean being so far out and so far away from the sun is the way that Jupiter pushes and pulls on Europa. And so as Europa orbits, pushes and pulls on different parts of Europa at different times and at different points in its orbit. That pushing and pulling creates friction inside of Europa. And you think about what happens when you create friction. A simple way we create friction during the winter is that we rub our hands together because it makes our hands warm. Same situation with Europa. It heats the interior and it allows it to maintain a subsurface ocean. And so here's Europa with its 3 sister satellites, Io, Ganymede, and Callisto, right next to Jupiter. This is not to scale. You see the red spot there, about 300 Earths, I believe, would fit inside the Great Red Spot. So this is not to scale. But we look at this and we see this bar on the bottom for tidal energy or tidal heating. And tidal heating really does play, it's you know, the type of geological activity and the amount of geological activity you have on each of the Galilean moons is directly related to how much tidal heating they get. You see Io, it has the surface that looks a lot like pizza. Io gets the most tidal heating from Jupiter because it orbits closest to Jupiter, and it is the most volcanically active body in the solar system. If you were to send a spacecraft to Io, whether you send it now or you send it 50 years from now, you're going to see hundreds of volcanoes erupting. We'll skip over Europa. We'll go to Ganymede. Ganymede is the largest moon in our solar system. It's bigger than planet Mercury. If it wasn't orbiting Jupiter, we call it a planet. But Ganymede gets less tidal heating than Io, but still gets some tidal heating. And so tectonics, not plate tectonics, but tectonics, the crust moves. And we see these streaks and these ridges on the crust. By the time we get to Callisto, poor Callisto gets no love when it comes to tidal heating. And so its surface, the type of the geological process that really is dominant on Callisto's surface is impact cratering. You see that there. So let's go back to Europa. Europa gets less tidal heating than Io, but much more than Ganymede. And you see that it's in a regime where it can have volcanism and tectonics. I call it a volcano-tectonic regime. And remember, Europa is 90% rock, 10% water ice. But what we're able to observe, the geological processes we're able to observe happen in the ice. So we have ice tectonics and we have cryovolcanism. And so just to give you a flavor of what we see here are some black and white images from the Galileo spacecraft that visited the Jupiter system and took these images of Europa in the early 2000s. We see on the top, we have these ridged plains in the background, top left, and then in the center, we see this circular region that looks like a smooth region. We believe that's a situation where we had mineral acids, specifically sulfuric acid hydrate, erupt onto the surface. On the top right, you can see we kind of have this feature that's shaped like a mitten. And in fact, that's what we call it. We call it the mitten. The correct name is Mirius chaos. But what we believe happened here was we had more of a slurry like fluid, more of like a slushy type fluid, and it pushed up against the undershell of Europa. It broke through, because remember, Europa has all these cracks and fissures on the surface, but because it was so viscous, it formed this curve-like shape. On the bottom, we have a feature called Thrace macula, and Thrace really doesn't look like anything special when you look at it at low resolution, but when you look at it at high resolution, such as you can see here where this yellow arrow is pointing, you see that it looks like hamburger meat in the center to me. And then it looks like at the edges, we've had some sort of cryolava flows flowing out. So that's really exciting. And one thing we're thinking about in sending our next mission to Europa is if we can get more images of Thrace. So that's effusive cryovolcanism. Here's evidence for explosive cryovolcanism, those geysers, remember. We have this double ridge on Europa at the top left, and then we can zoom in on the top right and we see these dark deposits. Europa is an interesting place. Things that have been freshly deposited onto the surface are dark. So the youngest features are the darkest and the oldest features are the brightest. And so we believe that this was fresh material that's been deposited onto the surface. It's likely salts or mineral acids. The reason it's darker because it's again, Europa sits within Jupiter's big magnetic field and it stains the surface. The bottom left, here it is in color. We have some reddish brown areas on Europa. And then on the bottom right, this is a lineated feature. These lines on Europa are actually called lineae. And being that my first name is Linnae, whenever I talk about Europa, people get such a kick out of that. But this is Rhadamanthys linea. And these white streaks, these white arrows again point to dark deposits where we think we had geysers that were just erupting along the line of the lineae and left these dark deposits. And so that's great. We've seen effusive volcanism on Europa or cryovolcanism with these flows. We've seen evidence for explosive cryovolcanism, but for a long time, all we had was evidence. And part of my dissertation was trying to figure out, we have evidence for explosive cryovolcanism. Why don't we see geysers on Europa like we see on Enceladus? And so I did my whole dissertation thinking about the heat transfer and the fluid mechanics within Europa and what would allow eruptions and what wouldn't. I also did a chapter thinking about if we build a camera to go on a spacecraft to study Europa, what it would take to be able to see geysers with that camera. And I was so excited about my dissertation, but I really thought I'm going to graduate from Johns Hopkins and people are going to think that I am a quack doctor because we have not seen these geysers yet. And then surprise, I did my dissertation. I defended in I think it was June or July 2013. And then by next Christmas, Lorenz Roth and his group had used the good old Hubble Space Telescope to make these observations of Europa. And these observations are on the bottom left. And what they saw was a transient atmosphere at Europa's south pole. Sometimes it was there, sometimes it wasn't. If you notice, here's October 99, you see something there. You see excesses in water vapor, just a little bit. November 2012, nothing's there. December 2012, it's back and it's in full effect. Europa is too small to hold on to its atmosphere. And even if it could hold on to an atmosphere, it's odd. It's not normal for a planet or moon to have an atmosphere just in one region. And we'd seen this before. Remember, I showed you the geysers on Enceladus. That's how they found the geysers on Enceladus. So when this paper was published, I was very excited. I knew that I would be hopefully gainfully employed for years to come because the geysers are there. And we're planning a mission again to go back and image them. This is just a cartoon on the bottom right, just a painter's description, or just, just a painting. So we have cryovolcanism on Europa, and that's very, very nice. But when you think about it, you have a water ice shell, and then you have salty fluid that moves up through that ice shell to erupt. And for that reason, people have thought this could be a problem. You have a buoyancy problem. Water-based fluids are not going to want to ascend through an icy shell because they're more dense. Also, how do you prevent water from freezing on the way to the surface? And so we think we've solved that problem. I see that have some questions in the chat. I'll stop in a minute, or maybe towards the end of that problem. So if we look at the bottom, Sarah Fagents, who was the first person to really think about cryovolcanism on Europa, she's a professor at University of Hawaii. When you think about explosive venting that's going to form these geysers, and again, you look at the way these geysers are drawn, looks very similar to a parabolic arc that learning about ballistic physics and calculus-based physics. What we know is that if we have a fracture and we put it on the surface of an icy moon and with water 90% of the way. So 90% of the fracture will fill with water. There's math and papers that talk about this. I won't go into it, but 90% of the way, it'll get 90% of the way to the surface. When it's 90% of the way to the surface, Europa has no atmosphere. It's zero pressure at the surface. So what'll happen is the volatiles in the water will want to spray out and it'll produce these ballistic eruptions. Also, we believe that Europa has water pockets in its ice shell, or salty water pockets. Remember, I talked about tidal heating and the gravitational pull of Jupiter that pinches these pockets. And we believe that when that pinching happens, excess pressure is created. The only way for that excess pressure to be relieved is for a fracture to be produced. And then in that, the fluid rushes to the surface. The third way, if we're going to think about effusive cryovolcanism, is that these water pockets are going to freeze over time. So they're salty water pockets. Again, they're going to freeze over time. And we know that ice takes up more space than water. So when they freeze, again, an excess pressure is created with the ice replacing the water. A fracture is going to be produced that'll relieve that pressure, and it'll push that water or that aqueous solution, it's salty water, to the surface. So we think we solved the buoyancy problem. So this is how we get these water-based fluids to the surface. For the case of supercooled versus superheated magma, I'll just try to go over this really quickly. These are pressure temperature diagrams for a basaltic magma and for water. I know they're inverted. This is the way that I like to look at them. And what's interesting is that magma, or molten rock, is a multi-component fluid. So you're gonna have it doesn't solidify just at one temperature like water does. It has several different temperatures at which different species in it solidify into rock. At water, you have liquid at 273 kelvins, below 273 kelvins, you have ice. And that's a problem, because as you release pressure and fluid moves from the interior of the Europa to the surface, it's going to want to freeze. So how do we fix that? Basically what I've been saying, we make a briny cryomagma by adding salt. And this is just what we do. You all know we do this in Greensboro, we do it in Maryland. When we don't want the roads to ice up, we pour salt or brines on it that depresses the freezing point. And so adding salt to water makes it, or mineral acids, makes it a multi-component fluid. And it depresses the freezing point so that these fluids can get to the surface without freezing. And there is math that backs that up. I won't get into that. But so that's how we get everything to the surface. And that's nice to think about. But is there observational evidence for salts on Europa? having been erupted. And of course there is. Here's our Gadnow Regio. Remember, the darker regions are the youngest, so these reddish brown regions. A team mapped our Gadnow Regio. On the bottom, you have a geological map. But they also, in addition to mapping it, they took the spectra of this region from the Galileo spacecraft that showed, we had spectra that was supposed to give us clues as to what the composition was. And they tried to mix chemicals and species in a lab to produce spectra that mimicked what we got back from the spacecraft. And what they found was, when they looked at the areas in our Gadnow Regio and the low albedo plains, remember, the stuff that's darkest or lowest albedo is youngest, what they found was that when they mixed compounds together, the low albedo plains, the spectra that matched the low albedo plains units, had the least water, but the most mineral acid and the most hydrated salts or brines. And so there it is. That's one example, just showing that these young regions on Europa, such as, if you can see my cursor, these reddish brown regions are basically brine. And we believe that we've had briny fluids erupt onto the surface. Okay, so we think we've solved both of those questions. The buoyancy issue and the issue of water wanting to freeze as it moves to the surface. So something that I've been looking at is, if certain features on Europa are created by just these eruptions of these effusive cryolavas, what rheologies do these cryolavas have? What's their viscosity? How fast do they run across the surface? And so we thought about that by looking at cryolava domes. And these are domes on Europa's surface. We don't think all domes on Europa's surface are created by eruptions of slush, but some are. And I've talked to you about how we think that the fluid will get to the surface coming from a fluid pocket in Europa's ice shell. But here are a couple of these domes, and the images were taken by the Galileo spacecraft. They're between 40 and 100 meters tall. They're 3 to 10 kilometers in diameter. That makes them intermediate in size between lava domes or volcanic domes on Earth and Venus. However, they are thought to have formed the same way. Sarah Fagents was the first one to model the formation of these domes using models that have been applied to the formation of lava domes on Earth and Venus. And so I'm PI of this project, and Sarah Fagents has been kind enough to work on it with me. It's good to have her experience. And so here's the math. So basically, we've explored a diffusion equation where we consider a time-dependent fluid viscosity. So basically what we do is we assume that slush quickly erupts onto Europa's surface, and then it quickly erupts, it'll pile up at the vent, and then it'll expand radially, and it'll kind of compress vertically to form these domes. So here's the equation that describes that. And we like this equation because it allows for a time-dependent fluid viscosity. Why do we care that the fluid viscosity is time-dependent? Because the viscosity of the fluid is going to get higher and higher the more it sits on Europa's surface, because it's going to get colder. So here's our diffusion equation. H is the thickness of the parcel of slush or fluid after it's all erupted onto the surface. Theta is a time transformation constant that includes a time-dependent viscosity. G is acceleration due to gravity. Nu naught is the initial kinematic fluid viscosity. So this is the fluid viscosity. It's erupted onto the surface, and then we start the model. So the viscosity at the time that all of the fluid has gotten onto the surface. R is the radial distance from the vent from which it erupts. And so that's our equation. Here's our solution to this equation. And we use this solution to make plots. And so I talked about a lot of these variables on the previous slide, but note that what we're looking at here is just the thickness of the fluid parcel as it moves across the surface and as time passes. That's why we have H as a function of R and T. V is the total volume of that fluid parcel. We'll talk about gamma on the next slide, which is the time scale over which the viscosity increases. And so this is our equation. We're able to put in a fluid volume, a fluid viscosity, and these are our plots that come from that equation. And this is, I'm being so detailed for the students. I know the professors probably understand. This is an axisymmetric plot, which means whatever you see on this side, you'd see mirrored. Whatever you see on the right side, you'd see mirrored on the left side. And so with that equation from the previous slide, we're able to obtain cryolava dome height as a function of radial distance from the origin at multiple time steps. So here we've put slush onto the surface. We look at where it's expanded to after 4.4 days, after 55 days, after 7 months, after 3 years. And we used a certain initial kinematic viscosity. And what we found was with this model, after 3 years, we're able to get a dome that's about 75 meters tall. It has a radius of about 2.5 kilometers. That's very similar aspect ratio and similar dimensions to these domes that are at the top of this slide. And that's wonderful. But we all know that we can use math any way that we want to, and we can, in theory, we can prove that anything would be so the interesting thing about applying geophysics to planetary bodies is actually being able to compare our models with observation. And so here are these domes. These are the same domes that were on the top of the previous slide. We actually have topography of them from the Galileo spacecraft back in the early 2000s. We've plotted the topography from Sarah Fagent's paper on top. And what we found is we have sort of a match, but not quite. What we want is we want these blue diamonds to match the red curve after 3 years. So this shows that we need to tune our parameters. Probably what we did here in this example was we either made the viscosity of the fluid too high, we didn't make it runny enough, or we didn't allow it to expand enough across the surface. But we think we're on to something. And NASA thought we were on to something too. This is a lot of words just to say we're still working on this model. I was able to get a solar system workings grant funded as PI, working with a lot of good people to perfect this model and make it so that the topography starts to match this red line. One thing we've also done, you'll notice when I described it, we assumed that fluid was quickly erupted onto the surface. And we didn't care how the fluid got on the surface. We didn't think about the eruption process. It just quickly erupted, and then we watched it form a dome-like shape. One thing that we've added to this with just the power of math and physics is actually being able to watch the fluid erupt from the vent and think about that and how that would affect the shape of the dome at the end, which is very important and is much more realistic to do. So we're very excited. About that. So, in order to get better constraints on our models, we need good high resolution images of Europa's surface. And we have medium resolution images. There were some issues with the instruments on the Galileo spacecraft that visited Europa in the late 90s and early 2000s. And I can talk about them, but basically what happened is they got into space, the camera, or not the camera, but the high gain antenna that was responsible for getting very high resolution images did not deploy. It was supposed to open up like an umbrella. Once it got to the Galileo system, it had been stored for several years. It got into space and the umbrella didn't open up. So we only got medium resolution images of Europa, but we want to fix that. We are sending another mission to Europa, the Europa Clipper mission, which I'm very excited to be on. I became a team member as a postdoc, and how many times it's not often you get to do your PhD on a moon. And then as an early career scientist, you're invited to work on a spacecraft that's going to get new images. And so this will get new high resolution images of our domes. So the Europa Clipper mission is a NASA flagship mission, which means it's the most expensive mission class that NASA has. This is a mission that at its cheapest was $2 billion. So it's much more expensive now. We've had cost growth and we've had inflation, of course. And so it's scheduled to launch in 2024. It feels like being on the mission team, we are working so hard to make sure that in 2024, we have the spacecraft on top of a rocket at Cape Canaveral, and we hope to go down and see it. So we're excited. I'm on the camera team. The camera team was selected in 2014. And we're launching 10 years later. So these missions are really a long duration thing. And when we think of instrument selections in 2014, the mission launching in 2024, that's actually really quick for a NASA mission. So we're working very hard. Our payload of instruments, our payload is just our suite of instruments, will work together to investigate Europa's habitability and its geology. Here's an artist's conception of what we'll have. We will have over 50 globally distributed flybys of Europa's surface under just under 4 years' time. The reason the spacecraft is it's flying by Europa, it'll zoom in, then zoom out, then zoom back in and zoom back out. The reason it's flying by instead of orbiting is, remember, Europa sits in the middle of Jupiter's magnetic field. And so we can't orbit Europa, or we would risk frying the instruments, frying the spacecraft. Those are your taxpayer dollars, and we don't want to do that. So that's why it's doing a series of 50 flybys instead of just orbiting Europa continuously. And so again, the overall goal is to explore Europa to investigate its habitability. The objectives are to characterize the ice shell and any subsurface water within the ice shell. Remember, I said we have fluid pockets. We want to characterize the properties of Europa's ocean, and we want to think about surface ice ocean exchange. So when the ocean upwells and gets onto the surface, we want to think about that. We want to understand the composition and chemistry of Europa's ocean, because right now we know it's salty, but there's not much else that we know. For geology, we want to understand the formation of surface features, including sites of recent or current activity. So those are those domes I was just telling you about, and characterize high science interest localities. If we look at this picture on the bottom right, here's the picture from the Roth discovery of the Hubble Space Telescope of those geysers from Europa. As I mentioned, I'm on the camera team. My role on the camera team is to actually find the geysers, work with others to find the geysers, and make sure our camera takes pictures of it. So it's a very exciting prospect, but also very scary. I was the youngest person on the mission when the mission was created. So they're trusting me with a lot. So here's our payload of instruments. The blue instruments are our remote sensing instruments. They're able to get data while farther away from Europa. The gold instruments that are surrounded in gold are our in situ instruments. We have to be very close to the surface, almost up on the surface, or have the spacecraft very, very close to the surface to get data. So we have REASON, which is an ice penetrating radar. It's going to help us find those pockets in the ice shell. It's going to help us know exactly where the ocean is. We have ETHEMIS, which is a thermal imager. It's an infrared imager. It's going to look for hot spots. A lot of times when we have geysers and we have activity on icy moons, it's accompanied by hot spots. We also have a magnetometer. We have a mass specs, which is our mass spectrometer. It's going to get the species it's going to tell us the composition of any species that are coming off the surface. And we have ICE, the Europa imaging system. That's our camera system. It's a dual camera imaging system. We have a narrow angle camera so that we can look at small patches of Europa surface at very high resolution. We have a wide angle camera so that we can look at wider views of Europa and put things into context. The principal investigator of that is Dr. Elizabeth Turtle at Johns Hopkins Applied Physics Lab. And so if we think about the camera system, this is the resolution we want to get for Europa. We don't have very many images from the Galileo spacecraft at this resolution. We have maybe 5 or 6. Remember, we had issues with Galileo. The high gain antenna didn't open up, so we couldn't get high resolution images. This is Marguerite Bay in Alaska. You can see these icebergs clearly. Why do we have to get this resolution for Europa? Because Europa has its own Marguerite Bay called Connemara Chaos, and Connemara is just here. It's about 70 kilometers across. It is a large area of icebergs, basically. You have icy plates that have broken up, they've rotated, they flipped over. We think what happened was that this is an area where the ice shell may be locally a little bit thin, and the ocean may have come up and kind of warmed things and broken these icebergs. That's on the left. On the top right, on the right rather, here's a 3D image of what it might look like, but we're excited to go there and get things in very high resolution. We're also, with the camera system, be able to get 3D images, if everything works the way that it's supposed to, of different geological features on the surface. Here's a double ridge, and we're very excited about that. I'm personally hoping we get 3D images of some of those domes that I was telling you about. So if we remember, Dr. Elizabeth Turtle, and I see that I need to wrap up, Dr. Elizabeth Turtle was the principal investigator on the camera system. Dr. Turtle is awesome. Not only is she the principal investigator on the camera system for Europa Clipper, she has her very own mission, the Dragonfly mission to Titan. It's wonderful to work with her. I've known her since grad school, so it's great to be able to work with her on these missions. NASA will also be sending a mission to Saturn's moon Titan. We talked about Titan with its very thick atmosphere. Again, we need radar to see to the surface of Titan. Here's Titan when Voyager 2 looked at it in 1981. before some of us who were on this call were even around. And here's Titan again, scaled to Earth and other planets and moons in the solar system. Note that Titan is bigger than planet Mercury. If it wasn't orbiting Saturn, we'd call it a planet as well. And it's pretty cold, has a 94 Kelvin surface temperature. It's the largest moon of Saturn. And we want to go there because it reminds us so much of Earth. Here's a radar image of sand dunes on Titan. With radar, everything that's smooth is, as many of you all know, is darker in colored. Things that are rough or elevated are brighter in colored. So here are our sand dunes, and we have some what I think is kind of elevations and crust in the sand dunes. We also have very Earth-like shorelines and lakes. These lakes are ethane and methane lakes. Why are we visiting Titan? Because we believe it has the key ingredients necessary for life. We can't go back and look at the complex chemistries that started life on Earth, but Titan is very similar to Earth. So we can go back and look at what's happening on Titan. It has energy, it has organic material, lots of complex organics. It has water in its interior as a subsurface ocean, but it also has methane as lakes. Earth has a water cycle, we have rain and we have lakes. So does Titan, but it's a methane cycle. And so I explained why we're going back to get at the prebiotic chemistry. Here's Dragonfly. Here's the capsule on the left that it's going to come down in. What we're going to do is we'll put this capsule on top of a rocket. We're going to launch in 2027. So 3 years after Europa Clipper, so lots of work to do. We're going to launch. Once the capsule gets to Titan, what'll happen is it'll open. Will land on the surface. On the right, the top right, we have, this is Dragonfly. It's our octocopter. It's about the size of a school bus. You see this circular thing that looks like ears. That's our high gain antenna to get the high resolution images. And while it's actually, if I back up, while it's coming down in the parachute, it's going to take images of aerial images. It's also going to take atmospheric profiles. When we get to the surface with our quadcopter, it's going to land here. Here's our landing ellipse. It's just south of a crater called Selk crater, S-E-L-K. We're going to have organic sand there. We'll have inner dune materials. And what'll happen is it'll land just south of Selk crater. It'll take data. It'll lift up and fly for about 7.5 kilometers, land somewhere else, take data there. And so over 3 years of exploration, it's going to have a total transverse distance of up to 180 kilometers. We're going to explore greater than 24 unique sites. And so it's pretty exciting. Here's our quadcopter again. We're going to look, or octocopter rather, we're going to look for prebiotic. We're going to look for prebiotic chemistry, habitable environments, search for biosignatures. Here's our payload of instruments. We have a nice geophysics and meteorology package, a mass spectrometer, a drill so that we can get those organics and sample them, a camera system, and a gamma ray neutron spectrometer. So we're really excited. And one reason that I'm happy to be sharing this with you all is that we have a student and early career investigator program, which is a program that I lead. And what we want is graduate students to come work with us for 2 years on a Dragonfly specific topic. This is created for graduate students. This program is created for graduate students who don't have a planetary science, geology, or astronomy background, who don't go to universities where there are programs. We're trying to train the next generation of explorers. Dragonfly will launch in 2027. It'll get to Titan in 2034. By then I will be much older and I am one of the younger folks on the team. So we need to train people now. Here are our students that we have. And you can see that we have 3 engineering majors, 1 physics major, and only 1 planetary science major. And that's by design. We are really trying to make sure that graduate students who may not have thought that they could apply their degrees to planetary science are doing so. Notice we have 1 student from FAMU. I'd love to see an Aggie come and work with us. And so if you're currently a graduate student or will be graduating this May and entering into a STEM graduate program in the fall, please join us and go to this website to see the list of current projects. The application deadline is May 27th. And there's FAQ. If you have questions, there's an email address. You send it to that email address. The questions will come directly to me and I will answer them. So that's Dragonfly. Finally, as I try to run through this, we've talked about the planets and moons in our solar system and how diverse they are. what can they tell us about exoplanets? These are all several moons in our solar system, very different geological processes. They're not in the classical habitable zone, but they are considered habitable when we think about Europa, Titan, and Enceladus. We talked about how tidal energy allows some of these moons to have geological activity and have internal oceans. And if that is the case for moons in our solar system, what about ice-covered exoplanets that orbit other stars? They could also be habitable. So I don't know that we necessarily need to look for other Earths to find habitable environments. We could just look for icy exoplanets that may have internal oceans. And what we want to do is find out what type of geological activity these bodies might have. And we hope they have cryovolcanism because it requires liquid water, it requires energy. Those are two of the necessary ingredients for life. And so if we could catch cryovolcanism, geyser-like plumes maybe being ejected from an exoplanet, that would be a sign that that an exoplanet was habitable. So what I and my collaborators did was we thought about the total internal heating of several planets and moons in our solar system, and we decided to plot that as a function of the size of these planets and moons. And we plotted some exoplanets, and we wanted to see qualitatively what could we say about bodies based on their internal heating and their size and their geological activity. We found qualitatively, after we plotted them, we're able to draw this purple line between Earth, Europa, and Enceladus, all of which we know are very geologically active. Everything above that line is extremely geologically active. Io, it plotted as, it's the most volcanically active body in the solar system. Early Venus had lots of volcanism. Coro 7b is an exoplanet that's covered with a magma-like surface. Everything below this line still had geological activity, but it was more subdued. When you got way below the line, such as Pluto's moon Charon, it's geologically dead. And so here's a better movie of that from the nice people at Goddard who make better plots than I do. And if we've heard of the TRAPPIST planets, TRAPPIST is a small star that has a tightly packed planetary system. We have these here. And what we find is that we looked at 53 exoplanets. According to our calculations, all of them should be volcanically active. TRAPPIST-1G and TRAPPIST-1H are probably large-scale versions of Europa with internal oceans, ice-covered surfaces, and cryovolcanism occurring there. And so that's really exciting. They may have cryovolcanism and geyser-like plumes. The rest of them may have volcanic activity. And so, again, we believe that a significant number of exoplanets may be cryovolcanically active ocean worlds, so souped up versions of the moons I've talked about. If space telescopes could detect the properties of explosive cryovolcanism, so if they could detect geysers or excesses in water on water-rich exoplanets, would suggest that planets have internal liquid water and energy, and could serve as a proxy for identifying habitable worlds beyond the snow lines of their respective planetary systems. And so I thought we were onto something. NASA did too. I'm the PI of a grant to study this a little bit more, to take what we know about planets and apply it to exoplanets. And so what I just want to leave you with is that as physics majors with a physics degree, you can contribute quite a lot to planetary science. A lot of planetary scientists have bachelor's degrees in geology. They don't do math and physics. So they are very excited anytime you can apply math and physics to something. And there are so many worlds in our solar system that you can study and contribute to. And so I want to acknowledge funding from NASA's Solar System Workings and Habitable Worlds programs, as well as the Europa Clipper project and the Dragonfly project. And I will stop there. I think we're after 5. I've been going for 52 minutes, and I think we may have questions. So I'll stop sharing, and if there's time, I'll answer a few questions. Dr. Cabetti, handing it back over to you.
Thank you very much, Dr. Quick, for this marvelous presentation. It is a common practice in our colloquium that we take pictures, still pictures, to remember this moment. So those of you you can put your video out. So let us your faces, and we can take pictures. So as you're doing that, there will be several questions. I believe Madison, one of our bright undergraduate students, has asked you a question. If you have read the chat.
Yeah, I don't know if she's still here, but I'm not sure what planet she's discussing. I was going so fast, if it can't hold on to the atmosphere, what causes it to come back? So I'm not sure which body she was talking about.
There was one picture that she showed from Hubble Space Telescope, where some stuff has appeared, and then later, a few months later, disappeared.
Right.
So that's
what makes it come back. So that's what I was trying to show. It's not an atmosphere. Those are geysers that are erupting. When geysers erupt from the surface of a small moon like Europa, they look like a transient, they look like an atmosphere that's there sometimes and gone other times, that's only on one region of the moon. And so it basically looks like an atmosphere that's flipping on and off. And it's only on one part of the moon. It's not globally surrounding the moon. And so it's geysering activity that's making it come back. When they're erupting, you have it there. When they're not, you don't see anything.
It is not seasonal.
It's not seasonal. Europa doesn't really have seasons. It doesn't have an atmosphere at all. All it has is geysers. And one thing that we don't know is the periodicity of those geysers. I've done models that try to make it seem like there's some period to try to figure out the periodicity. What we do know is that unlike Enceladus's geysers that seem to be erupting all the time, that's not the case for Europa, and we don't know why. And that's a reason to send a mission there.
I see.
Yeah.
Very nice. Any questions, please, from the audience?
Doesn't have to be about science. It could be about being a physics major and how that worked out. Questions or comments?
I just think that it was really cool that you got to do your postdoc on like a real mission.
Yeah, that was very nice. I consider myself very fortunate. So that just goes to show us, and I met the PI of the camera team while in graduate school at Johns Hopkins. So that just goes to show, always try to make a good impression, because people will remember how you act when they meet you. So I'm very fortunate to be working with Dr. Turtle.
Yeah, I've seen one of your presentations before too, last year, but I really like your work, and I think I kind of want to go into like this same thing. So yeah,
Please do. We need more people just like you. Are you an undergrad?
I'm a sophomore.
Okay, well, you can Google me. My bio shows up. I shouldn't say this, but NASA email addresses are public. Email me. See if you can do. I'm not taking interns this summer, but I usually do. I'm just taking a break because I had two interns last summer. So think about doing internships with NASA. Think about doing internships at Johns Hopkins Applied Physics Lab. And I can kind of tell you who's good to work with and who you might want to steer away from. So
I did an internship with JPL last summer.
Oh,
and
awesome.
I really that.
Who was it, Planetary, or was it another?
No, it was in like radiation effects.
Okay.
But it was really interesting.
Okay. Yeah. Europa Clipper has run out of JPL. So there are a lot of trips before COVID. There are a lot of trips from DC to Pasadena and back and forth. So JPL is a nice place. But yeah, we're looking, NASA's looking for interns like you. So please do keep applying and stay in touch.
Sekazi.
Yes, I'd like to thank Lene for such an excellent presentation, but I also put in the chat the fact that Lene received the Harold Urey Award from the American Astronomical Society, and I wanted everyone to be aware of that, and we all congratulate you for that.
Thank you.
And also I see that there's an asteroid that is named in your honor. Can you say something about that? I mean, your connection to that asteroid?
Oh, I have no connection to it. It was a complete surprise. I tell you, I talked about Dwarf Planet Series and how it has these salts on the surface. And I did this model to show how the salts moved from the subsurface, erupted onto the surface. And because of that, they decided to name an asteroid after me. And I did not know that was coming. Someone texted me on a Saturday and said, congratulations on your asteroid. And I said, what are you talking about? And so that just happened last summer. And it's a very, I think it's a small asteroid. What happens in planetary science is if you've done work on an asteroid or a comet a lot of times, and people think it's important enough, they'll name an asteroid after you. The asteroid is so small, I don't even know if it's Googleable. I don't know if it's on Wikipedia. So that's all I can say, but I do need to learn some more about it. Yeah.
Speaking of asteroids and names, probably you may like to know that 3 asteroids are named after Ethiopia.
Oh, awesome.
Just very recently.
Yeah.
Because Ethiopia is historically very well known in their astronomical work, not our history today. But there are also some legendary stories about Ethiopia. So people, I think the International Astronomical Union decided to name 3 asteroids about Ethiopia. Ethiopia is, by the way, a woman, okay? So
yes. That's wonderful to know. NASA is trying to be more mindful of making sure that when we name asteroids and when we name places on planets and moons, that we are being more inclusive, because for a lot of times these names just were not. Which is why we need more of your students to become planetary scientists like Vanessa. So because we think about things like that. So that's awesome, Dr. Kebede. I didn't know that about Ethiopia.
There is Madison. I think Madison just walked in, and there are two young women in my class, physics majors. Of course, there are also men who really want to do space science, astrophysics, probably planetary science. I left your email in the chat. Definitely, they will also have access to some of the documentation we have. I really like to apologize publicly. I think I misspelled your first name. Sorry about
that. It's okay. They can Google me. One thing that I ask is when I have a lot of students ask, how did you get here? Which I'm always happy to share. But I also have a Wikipedia page that goes into detail about that. So read that. And if there are questions, please do email me, connect with me on LinkedIn. We always want good students, just like the students that we have at A&T to come join us at NASA.
Right. Very nice. Professor Ashot, would you say a couple of words about?
Sure. I can say more than a couple of words. So wonderful presentation and wonderful science. I really enjoyed that. I have a question.
Sure.
But I just want to tell first that welcome back to the department.
Very nice.
I guess I remember you because
sort of, kind of, yeah.
Yeah. And also I want to welcome Dr. Sekazib to our department, please. Yeah, thank you.
Thank you.
Thank you for your so continuous interest and support of the department very much.
Yeah, sure.
Semi-scientific question. Okay. I can understand volcano when it's hot, but we are talking about 40 Kelvin volcano. Where this energy is coming from? Where?
Well, 40 Kelvin surface temperature. The energy comes from, when we think, it comes from radiogenic heating. Some of them still have radiogenic heating in the interior from their formation. When we think about Europa, that energy comes from Jupiter, because Europa is so small compared to Jupiter, and Jupiter's gravitational pull is so big that creates heat in the interior, and it has to get out some way. So that's the way it works with Jupiter's moons and with Saturn's moons.
What's temperature inside temperature? That metallic core is probably hot, huh?
It's it probably is. This is why we're sending more spacecraft to get data. But really and truly, it's the ice layer that's coming up and erupting onto the surface. So basically, when we have that tidal heating or that tidal dissipation that I talked about, a lot of that energy is dissipated within the ice shell. And so it has to get out some way or another from that ice shell. So that's what we have going on there, if that makes any sense at all.
Yeah.
Does that answer your question, Dr. Gasparian?
Yes.
Okay.
Thank you.
Thank you. I think a student had a question. I answered it while she was gone, Madison. So you were asking about Europa and that picture that I showed, where sometime it had an atmosphere and sometime it didn't, and then sometimes the atmosphere came back. So I was telling Dr. Kebede and everyone that that's not a real atmosphere. It looks like an atmosphere when you look at it from a telescopic image. It looks like an atmosphere that's turned on sometimes and turned off other times. That's what happens when we have geysers erupting from a moon. They look like an atmosphere, but they don't globally circle the moon. If you remember, the signal was on one area of the moon. If it was an atmosphere, the signal would be covering the whole globe. So anytime you have a small moon and you have a signal that looks very much like an atmosphere, but it's only in one region, sometimes it's there, sometimes it's not. It's probably cryovolcanism in the form of geysers. So good question. Were there any other questions?
Can you say something about habitability? What does habitability mean?
Sure. So when we think about the habitability zone of a planet, we basically mean that a planet is able to have liquid water on its surface, just like Earth does. But what we're finding when we look at these icy moons is that you don't have to have liquid water on your surface to have the ingredients that you need for life. You can have liquid water in an ocean under an ice shell, and organics the same way. That's what we have when we look at Enceladus, Europa, and Titan. And so nominally the habitable zone, when we think about on Earth is in the Goldilocks zone, not too hot, not too cold. And astronomers tend to look for other Earths. But if we consider that when we go past the Goldilocks zone and we go into the outer solar system and look at moons that are orbiting Jupiter and Saturn, they can also have conditions that would be amenable to maybe life taking a foothold there. We have to think a little bit further out when we think about planetary systems, not just find other Earths. If we could find other Europas and other Enceladuses, we'd be in a good spot.
Nice.
Yes. Any other questions?
Any more questions? I have one more.
Sure.
Please, first of all, everyone, if you want to take a picture with Lynette, please turn on your video. Okay. One question I have for you is, how do you see the future of space, in terms of research, in terms of, let's say, habitability and people actually spending time, not just a few hours for a year, or, not necessarily on the moon, just away from the moon, really far, okay? How do you see it? Say 100 years from now, will you be able to do this?
I think 100 years from now,
yes,
we might have stable lunar colonies. I'm not sure that I'm quite sold on terraforming Mars and living there. We haven't even been able to get lunar colonies and get that going. So I'm not quite sure that we'll within 100 years be past the moon. We'll probably have lunar colonies and we'll probably be traveling back and forth, but that's probably it. I think when it comes to extrasolar planets in other solar systems, we probably would have discovered so many habitable planets. The issue is it would take light years to get there. So in 100 years, we're not going to be there. But I do think NASA is investing quite a bit into ocean worlds, which are basically these icy moons that have ice, icy surfaces and oceans underneath. And I think in 100 years, we would have found so many ocean worlds, and it really will open up our eyes into what we think a habitable environment looks like. But I don't think I don't think we'll be in a spaceship traveling anywhere in 100 years, to be quite honest, at the pace that things go. And you have to remember that NASA, I see all these posts that talk about how NASA gets so much of the government's funding, and is it a waste of money? Well, NASA gets less than 1% of the government's total budget, and that's shared between astrophysics, planetary science, heliophysics, human exploration, which is the astronaut program, and earth science. And so we really do have a very constrained budget. So I don't know if something, even during the Apollo years, we did not have a huge budget, and we know that the budget has done nothing but decrease since the Apollo years. So I don't know if people wanted to divert funding from defense to maybe NASA. Maybe in 100 years we could do something like get terraform Mars or something like that. But the way that the budgets seem to stand now, I don't think that that's going to happen, unfortunately. So we take what we can get with our missions to Europa and Titan and be happy about it.
Yeah.
Yeah.
Thank you very much.
Thank you.
Additional questions? Students, you may ask about aliens. Are there aliens in space? Well, here is one. Okay. Okay.
Any questions? I saw, oh, okay.
No, I'm fine. No, I've already asked my question,
okay.
so I'm fine.
I thought I saw Madison turn her camera on. I don't know if that meant she had a question. If
it.
not, it's okay. I don't want to put you on the spot. If not, it's okay. Okay, no questions.
Doctor,
I do have one question that's not too technical.
Sure.
I was trying to take a picture, everyone. How do you keep people's names from disappearing? What does one do? Every time I get ready, I see your name. Every time I get ready to, click it, I have a Mac computer. So you do Shift Command 4 and get ready to take a picture and your names disappear. I know Professor James must know how to solve that problem. So I'll get him to show me later.
I don't know. I've seen people do that, and then we just had to tag it on Facebook later when we've had team meetings. So I don't know.
Just one introduction. We have an astrophysicist already on our campus, Dr. Melly. I hope she's here. So she's here. Okay.
Okay.
Melly, are you there?
Yes, I'm here.
Yeah. Say hello to each other.
Hello, very nice to meet you, Dr. Melly.
It was very nice talk. Thank you so much.
Thank you. I'm so glad to know there's an astrophysicist on campus finally. So
yes, we want to enforce the component again, astrophysics, solar planetary physics and everything. So we will try our best. It would be nice if you come back.
I'll come back for a visit now.
We will have a very good team.
I'll tell you what's keeping me here. My husband, in addition to loving Maryland, especially Prince George's County, Maryland,